All right, so this video kind of goes into finding 3D moments. So I posted a video about going over 2D moments without using the cross product because I think that's more time efficient. Um, but with 3D moments, you have to use the cross product because of the addition of the Z component. So the definition of a moment obviously doesn't change. It still has how a force causes the rotation about a certain fixed point. So like the thought about the door handle still works. The thought about the hinge works. All of the like the leg example I brought up last time still works. All of that thought process fundamentally is still valid. Now you're just using a different equation. And that's the equation that you use right here. And it's just the cross product of a position vector that relates the point that it's rotating about to some point on the line of action of the applied force. And then you cross that with the force vector. And this force vector comes from the procedure we learned in lesson 3. So that's super important to be comfortable with because that's going to keep coming up. So kind of jumping into it, the important thing to realize is that you can make these problems really, really easy on yourself and really simple and quick by choosing the correct position vector. Because the line of action of a force has infinitely many points along it, but there's definitely a handful of points that make this process easier. And that kind of jumps into step 1. So, step 1 is to find the easiest point that connects the point that it's rotating about with the line of action of the force. So essentially, like I said, there's infinitely many points on that line. So you could use whichever point on that line as long as it exists on that line. But usually, the way to make this problem easier is to implement as many zeros as you can into that position vector. So essentially, what you would want to do is you would want to find something that lies on some sort of like axis, generally even the same axis as the point that it's rotating about. So that's going to take some practice, but again, you don't necessarily do anything negative by picking a point that's not or that doesn't have as many zeros as possible. You just end up doing more work. So again, step 2 is exactly what we did in lesson 3, where it's finding the force vector. And I'm not going to go too deep into the details of that because I already have a video on that. But essentially, you just find the position vector connecting the head and the tail of the force itself. So this is separate from the position vector found in step 1. So that's the part that a lot of people get confused with, is that these are not equal. So these are not the same position vector. So that's something to remember. This one is specifically related to the force itself. So don't get that confused. But then you go through the same steps that you normally did. So you found the magnitude of the vector you found in step A, and then you divide this step and get the unit vector, and then you multiply some magnitude that's given in the problem into the unit vector to find the force vector. So that's the same steps as shown in lesson 3. This part is what I really wanted to go over because there were a lot of people in the notes who said that they weren't exactly um, comfortable with this. So basically what I'm going to do is show you how to do the cross product by hand, and then I'll post a separate video of how to program and implement your calculator for this procedure. So basically you do it by component. So you set up this little matrix, and the first column talks about all of the x components. So you have your little I, and that should have a caret on top. So you have that I, and then you have the x component of your position vector, and then the x component of your force vector. And then you have your y components of everything, and then your z components of everything. And something I wanted to point out is that in this situation, order matters. So this first one up here has to be the position vector, and the second one here has to be the force vector. You can't do force on top, position on the bottom. So that's super important to remember. But after that, you just kind of go through and say, all right, if I'm finding the I component, right, which is this column here, I ignore these values and look only at the ones in these columns, right? And then think of it as an X, right? I do that and that. So I make an X inside of this problem. So for the I component, it's going to be Ry times Fz minus Rz times Fy. Now, if I can erase all this without erasing everything else, that'd be great. Okay, cool. So for J, I'm going to ignore these components. So those come out of the problem. And then I'm going to do another X inside of the other remaining problems or components. And then I just do that. So then it's Rx times Fz minus Rz times Fx. And then again, same thing applies. I'm going to do the K component. So I ignore these now. And then I'm going to make my X here. And then it becomes Rx times Fy minus Ry times Fx. So again, you ignore the column for the component that you're solving for. So in the I component here, we ignored the I column here. And then in the J column here, we ignored the J column here. And in the K column here, we ignored the K column here. So that's one thing to remember. You ignore the column you're looking at. But again, in this case, order matters because of that subtraction sign. So because of this subtraction sign here, you have to make sure that you are in fact going top left times bottom right minus top right times bottom left. So you have to make sure that you're multiplying them in the correct order. So it's always this minus this every single time. But other than that, this becomes your, oh wait, that's not how you do it. This becomes your force vector. Another thing to remember is that this J term should be negative. I don't know why. It has to do with right-hand rule, with which quite frankly, I never really learned. But that is definitely something to remember in this formula. And that's something that you build into the calculator answer that you get. So similarly to when we did forces in 3D, you end up having it in terms of these components. So there's already a magnitude and a direction built into it. This entire section will end up becoming a number. So basically what you're going to end up with, what your answer should look like, your final answer should be some number for the x direction, some number for the y direction, and then some number for the z direction. And then you need units, so it's either going to be Newton meters or foot pounds. You need some direction, so clockwise or counterclockwise, and then you need a point of application or like a reference to whatever your hinge was. So about some point. So again, this is your units, and that is your direction. And then this is, this is your point of application. And actually, now that I think about it, this is not relevant in 3D because you already have that reference to the direction built into that vector. So I don't believe that you need the clockwise counterclockwise thing because it doesn't necessarily make sense in 3D. So this is your magnitude and your direction. So that's another thing to remember is your final answer form. One last thing I wanted to bring up is how you can figure out the units without explicitly remembering them. So the moment equations are either force times perpendicular distance or R cross F, right? Either way, you're relating some force and some distance. What are the units for force? What are the units for distance? So these, by multiplying the components, you're multiplying the units as well. So that's how you can find the units without necessarily memorizing them or verify it if you have any doubts. But again, that is essentially the summary of the 3D moments lesson. I will post, probably not tonight, but shortly, the video for programming your calculator. And then the video for couples. So, yeah, I'll see you guys later.